prevented. Okay, but this is a very classical example of how spoofing could be used in a very simple manner in order to have a very, very large result on the network. Now, additionally, if we look at this just from a bandwidth point of view, let's say, for example, that this device, router 1, has this serial link that is going out to the internet. Let's say that this is a T1 link. Now, with this T1, we have the attacker using the amplification segment, so we send one request, we get tons and tons of replies. It's really not going to take that much traffic in order to fill up that full T1 link that router 1 is using. So this type of attack, it could be on the actual end host itself, like the server, or it could be against the network just trying to use all the available bandwidth until the result is that there's a denial of service on the actual network. Okay, so you'll see there's lots of different sub-variations of the denial of service attack. Smurf and Fraggle are just one, but a lot of the times they use IP spoofing because it makes it harder to track where the attacker came from in the first place. Okay, this is also very common with distributed denial of service attacks that use something like a botnet in order to have lots of sources sending the packets. If we're sending it from some unknown source, then it's going to make it that much harder in order to track it back to the offending host and fix the problem in the first place. So when we get to the actual iOS, we're going to revisit these different attacks and look at the actual methods that we can use to prevent them. A next one that we have would be attacks against the control plane of the network. Control plane basically means the protocols that need to run in order for the network to run in the first place. So control plane would be something like BGP or OSPF, EIGRP, the type of stuff that's in the network but kind of behind the scenes, that's really running what's going on in the background. But if any type of attack happens to the control plane and the control plane goes down, it implies that the data plane, which is the actual packet forwarding, that is going to go down. So if I can trick a router into dropping its BGP sessions on the internet, it will not have any routing information and it will not be able to route any packets. So these type of control plane attacks, usually they are used for denial of service, because once routing goes down, it means that all of the packets that are going through that router are going to go down. A classic example of this is the TCP reset attack that could happen against BGP. Now, BGP, the Border Gateway Protocol, we're not really going to get into a lot of details about that. But in a nutshell, basically you have two systems, usually they're two routers, that are running this BGP relationship with each other. So they're exchanging routes that are for the internet. Okay, so they're going to be sending tons of routes to each other. It's somewhere in the order of 200, 300,000 routes that are out there on the global table today. Now, normally, with the normal operation of BGP, if I am routing with another router, I know particularly what is their IP address that I want to send my updates to. So let's say, for example, that my IP address is A, and I'm running BGP with someone's address who is B. So when I receive a BGP message in, I would assume that the source address is supposed to be coming from them. It's supposed to be coming from B. Now, the way that we could use spoofing to attack this operation of BGP is that if someone pretends to be that host, they pretend to be B, then they will be able to change whatever information that I have in my BGP table. So they could add routes, they could delete routes, or worst case scenario, they could tell me just shut the BGP session down, which is a TCP reset. Basically means just drop the connection, and then you lose all the routes in your routing table. So there's a lot of simple ways to prevent this type of attack, but again, if you don't know that it's there in the first place, you have very, very huge vulnerability to your network. So let's say, for example, that you have two connections to two different service providers. And on your network edge, you have a router that's running BGP. I have a BGP peering with AT&T. I have a BGP peering with British Telecom. and I'm using these two service providers to route my traffic out onto the internet. Now, if someone on the internet sends a spoofing attack to me, pretends like they are the AT&T router and says reset the session, they pretend to be the British Telecom router and say reset the session, I now have no routes to the internet. Now it's a complete denial of service against the entire company. So the risk factor that goes into these type of attacks, it's very, very large unless you understand what are the vulnerabilities and what are the different ways that we can prevent these. So again, when we get into the command line a little bit later, we'll talk about what are the different ways that we can stop these attacks. Okay, man in the middle, I'm not going to talk about that much right now because we will talk about that when we get more to some of the layer 2 attacks and some of the other layer 3 options that we have for mitigating these on the routers. Okay, the other portion that is worth mentioning here that relates to the IP spoofing attack is that if someone is trying to spoof a TCP session. Now we know the way the TCP IP stack works is that there's other protocols besides TCP. There's protocols like UDP, there's protocols like RTP, reliable transport, that's used for voice calls. But realistically, the vast majority of traffic on the internet is TCP based. TCP runs applications like web browsing, like SQL. Vast majority of stuff is going to be based on this because TCP is a reliable transport. It means that if something happens and a packet gets dropped, TCP can deal with that. Okay, other unreliable transports like UDP can't necessarily deal with out-of-order packets or packets being dropped. Now, when we are looking at an attack against TCP, there's an additional layer of complexity that the attacker has to deal with. It has to do with how the retransmission and how the reliability of TCP works. And it uses something that is known as the TCP sequence numbers. So let's say, for example, I am a client running a web browser and I'm trying to connect to cisco.com, connect to the web browser. First thing I'm going to do is send a TCP open message to the web server saying I want to start the session. Okay, this is known as the TCP SYN for synchronized, S-Y-N, TCP SYN. So I ask the web server, can I start a session with you? They reply back and say, yes, you can start the session. I also want to start the session with you. Okay, that's the second portion of the handshake that is known as the TCP ACK, the acknowledgement. So they're telling me, yes, you can start the session, and they're also going to send me an additional SYN. So they're saying, yes, you can start the session, that's the ACK, and also I want to start the session with you. So it's a mutual agreement that we're going to start the data transfer. Third step of the three-way handshake, I reply back to them with an acknowledgement saying, I got your request to also start the session. Okay, so once we go through that three-way handshake, now the session is open. Now I can send HTTP GET or whatever commands I want to start browsing the web pages. Now once the actual data starts coming, for every packet that I receive from the server, there's going to have a specific number associated with it, the sequence number, that determines if the packet is in order, or if the packet is out of order, or if the packet is not even belonging to my session in the first place. Okay, this is what the sequence number is used for. It's to make sure that the packets, if they arrive out of order, we can reassemble them in the correct order, or if something gets dropped, we can detect that and try to retransmit the packet. Now the problem is, from an attacking point of view, is that if someone jumps in the middle of my communication between my web browser and cisco.com and they want to pretend like they are Cisco's web server, they're going to have to know what the sequence numbers I was using with the server were. Because if they're not in the range, which is known as the TCP window, if they're not within that TCP window of what the sequence number should be, I'm just going to drop the packet when it comes back in. So when we're looking at spoofing attacks that have to do with TCP, we can put them into two different categories. They're called non-blind spoofing and blind spoofing. Non-blind spoofing means that whoever is trying to accomplish the attack, they can see all the communication between me as the client and the server. Now, since they can see all the communication, they can also see what are the sequence numbers that we are using. And this is really where the danger comes in with this type of attack. Because if they know the source and destination is, so they know my address, they know the server's address. They also saw our initial negotiation where we went through that three-way handshake. So based on the handshake, the attacker now knows what is the sequence numbers that are supposed to be going back and forth. So what they could do is one of two things. They could now pretend to be the server, which would be spoofing the destination from my point of view, or they could pretend to be me. Now the problem with this is the end result is what's known as a packet injection attack or a session hijacking. So this would be used if I'm sending them some sort of request and the attacker wants to redirect me to another website. Let's say they're doing some sort of phishing attack and they're trying to get my password. So they pretend to be the web server and they send me a dialog that says authentication failed, re-enter your password. I say, well, I must have typed the password wrong, so I type it again and it actually goes to the attacker, not to the legitimate destination. So the issue with this attack is that if you run into a situation where the attacker is actually in the transit path, so they can see all the traffic from the source to the destination, it becomes much more risky because it's not actually that hard to figure out what the sequence numbers are supposed to be. It's a fairly easy attack to implement when you look at a lot of the tools that are out there today that are used for sniffing packets and then for doing a type of session injection. Okay, the other end of the attack would be the blind spoofing, which basically means the attacker has to guess what the sequence numbers are. Now this one is less likely to occur, but it's still a potential issue that we need to be aware of. And this would relate to the attack against BGP a lot of the times. So if someone is trying to do a reset attack, basically means they want to turn off BGP on the router between two neighbors, they would try to guess what the sequence numbers are supposed to be just by sending random packets to the destination. So with the blind spoofing, you're not as much of a risk of a session hijacking attack, which would be someone actually intercepting the data. You're more at the risk of what's known as the session termination or the reset, which just drops the communication between the neighbors. But unfortunately, when we look at IP as a protocol itself, there's nothing built into the TCP/IP stack that is going to prevent this. So just like the IP spoofing itself, which is going to be at layer 3. So layer 3 of the OSI model, that's where we would have our source IP address and our destination IP address. Or at layer 4, at the transport layer here with TCP, where we're getting down into the detail level of the TCP flags like the SYN, the reset, the push, and also the sequence numbers. So a little bit later, when we look at the individual applications that are vulnerable to this, we'll talk about different ways to prevent this. For example, with BGP, the easiest way to prevent this is just to use a password between the neighbors. It sounds like a very simple fix, but you'd be surprised how many times this has actually happened in the internet where reset attacks have successfully worked on different networks. Now with the session hijacking for the non-blind spoofing, that gets a little bit harder. Usually the fix for this type of attack would be maybe to run SSL or to run IPsec, so your communication is actually encrypted between the endpoints. Then it wouldn't really matter if someone did spoof TCP, because you have a higher layer application on top of that that's still going to do some sort of integrity checking. Okay, any questions up to this point on either the IP spoofing or the TCP spoofing? And again, we will come back to the individual variations of this later when we talk about the different tools that we have on the routers in order to fix these type of vulnerabilities. Okay, and actually here we have some of the methods to prevent them. It says, since there are many ways to implement spoofing for different purposes, there are many different ways to mitigate it. So a lot of different options I have listed here. really depends on what type of attack you're trying to do in the first place. Okay, one of the very basic prevention mechanisms is what is defined by a request for comment, the RFC 2827, network ingress filtering, defeating denial of service attacks which employ IP source address spoofing. Now, if you want to read this in detail, you could just Google RFC 2827, or if you go to the site rfc-editor.org, that's rfc-editor.org, that's where these are actually hosted, the RFCs. You can look that one up. It talks about why IP spoofing is a problem in the first place. Okay, like I talked about, because the IP stack does not have any protection built in, and then what you could do to prevent this. Okay, 2827, one of the ways to implement this is going to be with an access control list. So tomorrow we'll talk about this when we look at both standard ACLs and extended ACLs, and you are looking at your border router that would be connecting to the internet or connecting to whatever other transit network you're using. There's some basic protection mechanisms you can use to prevent people from outside the network trying to spoof addresses on the inside of the network. And when we look at the end logic, it makes complete sense on how the recommendation works for being implemented. The problem is that if you didn't know the problem was there in the first place, then you wouldn't know to fix it. So with any of these security technologies, it has to do with you as a security administrator being very proactive about trying to figure out what are the different vulnerabilities out there and what are the best practices recommendations that I need to apply onto my network in order to prevent these problems. Okay, next one here, unicast reverse path forwarding. That's going to go along with these access control lists. So tomorrow when we get into ACLs, I'll talk about that in a little bit, or talk about that in a little bit of detail and see how we can prevent the spoofing with that. Now from a layer 2 point of view, when we look at the catalyst switches and talk about layer 2 attacks, we'll look at these next 3 tools, the address resolution protocol inspection, that would be for our layer 2 Ethernet MAC address, to layer 3 IP address mapping on the Ethernet LAN, how we could use inspection of the ARP protocol to make sure that spoofing doesn't happen on the Ethernet segment. Okay, DHCP snooping, IP source guard, those are also going to go along with that to prevent spoofing on the Ethernet LAN. As I mentioned with BGP, routing protocol authentication, this also goes along with any of the other control plane protocols in the network. So if you're using OSPF for routing or you're using EIGRP for routing, one of the basic mechanisms that are built into those are secure authentication based on algorithms like MD5, where when I receive a routing update from my neighbor, I run a basic MD5 hash on the password that they're sending, make sure it matches up with my own. If they are identical, then I will accept the information that they're sending me. So even if someone on the network is spoofing, it's not going to make a difference because they don't know the password in the first place. Okay, so then they would have to go above and beyond just basic spoofing. They would have to know the 2 different pieces of information, the password and the spoofing information. Okay, BGP time to live security. This is a very interesting feature that actually prevents a lot of attacks that happen onto BGP. And if you are running BGP in the network, you definitely do need to do more research onto this, because just with its default configuration, BGP is actually very vulnerable to a lot of these different types of attacks. And if you're running BGP again, it means you need BGP to route to the internet. So if someone knocks out your BGP control plane, most likely means that you're completely isolated from the rest of the world. And if you're routing to your own corporate sites over the internet, doing some type of e-commerce, then definitely that's going to be an issue with downtime. So again, that would be an attack against the availability of the network. Okay, another one we have is to check the IP options. Now we'll talk about this a little bit later today, probably after lunch here, when we get into the security audit feature of the SDM and look at some of the minor switches and services that are on the routers, about how it processes different IP packets. One of them is a field that is in the IP header, or could potentially be in the IP header, that is known as the source routing field. Now, in today's networks, I could not come up with a single example of why this is legitimate, of why some legitimate application would actually use the source routing field. Pretty much the only thing that it is used for today is for network attacks. So generally, you would tell the router to check this, and it says if this option is set, if source routing is on, you want to drop the traffic. But that in and of itself doesn't really say much. We're going to talk about in detail why you would not want to use source routing, because it's used along with spoofing to accomplish what is known as a man-in-the-middle attack. That would be an attack on confidentiality, where someone is pretending to be the legitimate destination or pretending to be the legitimate source in order to do whatever attack they're trying to get. They're trying to get your financial information or your passwords, whatever. Okay, then last but not least, IPsec VPN or an SSL VPN. If traffic you're sending over the network is encrypted and you're doing a hashing to make sure it's legitimate, then a spoofing attack is not going to help them at all. Because unless they know your IPsec keys, which is in today's networks, if you use the recommended implementation, it's very, very, very unlikely that it could be broken. So of course here, this list is not going to be completely exhaustive of what are all the different techniques, but we do definitely want to know what are the common problems in the network and then the common ways to